The smooth, continuous transition from vibrant red to deep purple is the visual signature of a neutralizing chemical reaction. Our objective is to execute this process under controlled conditions, using a liquid indicator to track the pH scale from a strong acid at level 1 to a strong base at level 11. When handling corrosive 0.1 molar hydrochloric acid, safety is the first priority. You must wear safety goggles, a lab coat, and gloves throughout the procedure. Prepare a 250 milliliter beaker, a set of clean test tubes, and graduated pipettes. By combining these safety protocols with precise measurements, we can transform a hazardous reaction into a quantifiable, observable experiment. Begin by measuring exactly 200 milliliters of the hydrochloric acid into your beaker. To see the acidity, we use a universal indicator. Adding 100 drops maps our solution against the scale. As you stir the indicator into the acid, the liquid turns red. This confirms the slider's position at level 1. This red state provides our starting baseline, an environment of extreme acidity. Establishing this red baseline is a prerequisite for the titration. Without a clear starting point, we cannot accurately measure the subsequent color shifts. To begin neutralization, transfer 10 milliliters of your red acid solution into a clean test tube. Our neutralizing agent is 1 molar sodium carbonate, often referred to as washing soda. It is critical to use separate, segregated pipettes for your acid and your base. Cross-contamination at this stage will compromise the accuracy of your results. Using the titration technique, introduce the sodium carbonate 1 drop at a time. The reaction begins the moment the base makes contact with the acid. If you introduce the base too quickly, the liquid will bubble over the test tube, skipping the intermediate stages of the color spectrum. Precise mechanical control over these drops is the only way to isolate and observe each specific pH state as the color shifts. The bubbling you see is effervescence, the active production of carbon dioxide gas as the acid and base react. This gauge tracks color against numerical data, starting in the red zone, pH below 3. As acidity weakens, it shifts to orange, then yellow. Green marks pH 7, neutrality. Adding more base shifts the solution into the blue range, pH 8 to 11. Temperature is a significant variable. High room heat increases the reaction's kinetic rate, causing colors to shift too fast to track accurately. Maintaining room temperature prevents a pKw shift, the auto-ionization of water, which keeps your color transitions stable and predictable. This color sequence provides a real-time visual map of the chemical neutralization occurring inside the tube. You have reached the endpoint when the carbon dioxide effervescence stops and the color remains constant. The final steady color is purple, indicating a strongly basic solution with a pH greater than 11. At this stage, the base has completely neutralized the original acid. For higher precision, you can use a digital pH sensor to log the exact numerical values during each color change. You can also apply this indicator to a standard baking soda and vinegar volcano to see these color shifts in a more dynamic flow. Once the experiment is over, follow safe disposal protocols. Rinse the basic solutions down the drain with plenty of water and clean all glassware thoroughly. Mastering this procedure provides you with the mechanical control and monitoring techniques required to perform accurate titrations in the laboratory.